Unit 3, VC Chemistry, Area of Study 2. Today's section, we will look at equilibrium law. So with equilibrium law, we will be able to numerically determine what reactions are reversible and what reactions are not reversible. And we'll also focus on how the equilibrium law defines equilibrium expressions and therefore leading to equilibrium constants. Okay. At the same time, we'll discuss how to calculate the constants and its units. Okay. So before we define equilibrium constants, we need to define a new idea that's called reaction quotient, QC. Okay. For a reaction, this is a blah 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 reaction, the reaction quotient is defined as the multiplication of the concentration of products to the power of its coefficient over the multiplication of the concentration of the reactants to the power of their respective coefficients. Okay? So here in this expression, the square brackets are used to represent concentration. If you recall this kind of notation in Unit 2 when we talk about pH, okay? The value of QC will change as the reaction goes. If you imagine if this reaction goes forward, initially there might not be many products, but there are a lot of reactants. So your QC would be small. If the reaction keeps going forward, then products keeps being produced and reactants consumed. As a result, your numerator is getting larger and your denominator is reducing. Therefore, QC will increase as the reaction goes forward. Okay? And if you think about it, if it's a reversible reaction, again, QC can also change as well. Okay? So QC is not a set number. It will change as reaction goes. There is an interesting observation of QC. For a reaction to produce ammonia at 400 degrees, we have 4 different mixtures. And this reaction is famously a reversible reaction. Okay, this reaction is never complete. Okay. So at 400 degrees, when it reaches equilibrium, there are 4 different equilibrium mixtures. You can see that in the first mixture, there are 0.25 molar concentration of nitrogen and 0.75, and resulting in that much of ammonia. Yeah, as compared to reaction mixture 4, which is completely different numbers. But when the temperature is 400 degrees, all the 4 mixtures arrives at equilibrium. And what we did was we calculated their QC at equilibrium. And surprise, surprise, their QCs are almost the same. Almost the same, okay? So it seems that even if the concentration of reactants and products at equilibrium are different from each other, if you look at this column vertically, they're all different, yeah? But somehow, when you write the QC of all the 4 mixtures, yeah, the proportion, which is basically what QC is, right? QC is a fraction, so it's a kind of proportion of products over reactants. The proportion of products over reactants are almost the same, okay? So based on that observation, we defined that QC as equilibrium constant. So what is equilibrium constant? It is when a reaction mixture reaches equilibrium. Yeah, that QC, that value of QC, is defined as the equilibrium constant. Why is it a constant? Because whatever the component is, as long as this mixture is at equilibrium at that particular temperature, the proportion, the concentration fraction are always the same. If they're the same, we call it a constant. Okay? So the equilibrium constant. Therefore, Kc and Qc have the same expression. The way we write the expression for QC is how we write expression for KC. The only difference is that QC will change before the reaction reaches equilibrium, and the value of KC is only one. That is, when this reaction mixture is at equilibrium, and that value is the value of KC. Okay. So in the future, we'll be working more closely with equilibrium constant rather than trying to capture a reaction before it reaches equilibrium. Okay. So the units of equilibrium constants depend on the expression used to represent the chemical reaction. So it's actually dependent on the chemical reaction itself. Okay. So for a given reaction, Kc is only subject to change in temperature. If you change the concentration of particular reactants, doesn't matter. When the system reaches equilibrium, Kc will always be the same. Unless if you change the temperature, then Kc will change. Okay. So the value of Kc, this allows us to predict the extent of the reaction under a given temperature. If you think about it, if under the same temperature, all equilibrium systems of a particular reaction will reach the same Kc, then we basically know the proportion between products and reactants at equilibrium at that temperature for a particular reaction, right? However much reactants you add into the system, the proportion, the conversion rate, or at the end, the percentage of the reactants to be converted to products remains the same. So it's quite abstract. Let's try an example. In this case, write the equilibrium expression and determine the unit for Kc for this reversible reaction. So we said the expression for Kc is exactly the same as the reaction for Qc. So it is a multiplication of the concentration of all the products to the power of their coefficient over the multiplication of concentration of the reactants to the power of their coefficients. So the Kc in this case would be written as this. Yeah. And what is the unit? You substitute the unit of each component, each item in the Kc so as to calculate the overall unit. So in this case, there is one m at the bottom that wasn't cancelled out. Therefore, the Kc has a unit of m to the power of -1. So remember, Kc tells the proportion of products over reactants. So that would help you to remember how you write an equilibrium expression. Okay. Then how do we calculate the Kc? Let's say in the following expression, okay, or following equation, the concentration of each species at equilibrium is given as such. So can you find the value of equilibrium constant? So we already have the Kc expression, we just need to substitute different numbers in. Okay? So substitute the values for each into Kc expression. We will have a result to be 0.83 mole to the power of -1.